Hello everybody, today I'm going to explain what is phase of a sound wave using augmented reality. Alright, let's dive in. Alright, so before we talk about phase, let's talk about a periodic motion. Now let's consider the sinusoidal oscillation. It is periodic in nature. The reason why I say it is periodic in nature because it repeats itself in equal intervals of time. Now this x-axis represents the time axis and the y-axis represents the amplitude. Now let's consider the sine wave. It starts out from the origin, which is the mean position, goes up to the positive extreme, then comes back to the mean, goes to the negative extreme, and then comes back to the mean position again. Now if you observe from this point onward, it repeats the same cycle as it did before. This is why it's a periodic motion, because it repeats itself in equal intervals of time. We need a term or a quantity to describe the position of a point in this periodic wave, and that's exactly where phase comes into play. Phase literally describes where the point is located in the wave. It is very useful to describe and define the phase relative to a reference point. I stress the word relative here because phase is relative. It is not absolute, meaning phase can be defined only when compared to a reference point or a point of interest. Phase is usually measured in degrees or radians because it's a measure of angle. And now that we have defined phase, there is a new definition of wavelength here. In the previous video, I defined wavelength as the distance between two crests or the distance between two troughs. But in fact, the latest definition of wavelength with the insight of phase is that it is the distance between two consecutive points that are in phase. Meaning, if these two points are in phase because they're going to go up no matter what, and they're consecutive, meaning one after the other, and that distance is a wavelength. For example, the distance between these 2 points is also the wavelength because they're going to go down consecutively. Alright, now that we have talked about phase, let's talk about phase difference. Now, phase difference, as the name implies, is the difference in phase between two periodic waves or 2 points in a wave. Now, the phase difference can be positive or negative. A positive phase difference indicates that the wave of interest is leading the reference wave. And a negative phase difference implies that the wave of interest is trailing the reference wave. Now, let's look at some examples of phase difference. Alright, so in this example we have 2 waves and clearly they're not in phase with respect to each other. So let's consider the black wave first. The black wave starts from the origin or the mean position, goes up to the positive maximum and then goes back to the mean position again. So when the black wave is at the positive maximum, the blue wave starts from the mean position. And by the time the blue wave hits the positive maximum, the black wave is already at the mean position. So we can observe here that the blue wave starts when the black wave has finished quarter its cycle. Because one cycle for a black wave is starting from here and ending up right here. So this is like a quarter of the cycle, and when you say quarter, it's one cycle represents 360 degrees or 2 pi, so quarter is pi by 2 or 90 degrees. So we can infer that the phase difference between these 2 waves is 90 degrees. And clearly, the black wave is leading the blue wave and not the other way around because the black wave was generated first in time followed by the blue wave. Alright, here's the second example of phase difference. In this case, again, we have 2 waves, which is the black wave and the red wave. But in this case, the red wave starts after the black wave has completed half its cycle. In this case, black wave has already completed 180 degrees or pi radians. And we can infer that the phase difference is pi radians or 180 degrees. But it's also interesting to note that, both the black waves and the red waves follow the same cycle, but they are mirror images of each other. So they completely cancel out, and it's also referred to as completely out of phase. Here's a third example. Again, we have 2 waves, black wave and the green wave. And the green wave starts after the black wave has completed one full cycle. So we can infer that the phase difference is 360 degrees or 2 pi. But in fact, the green wave and the black wave are in phase, so there is no phase difference. because in this case, here the green wave is overlapping the black wave. And if you can compare these two regions, the green wave and the black wave are synchronous. They're in phase no matter what. So this is a perfect example of in phase or no phase difference. It's possible to predict the behavior of waves when you know the phase difference. For example, if the phase difference is n pi and n is 0 or even, the waves are bound to be in phase. And consequently, if n is odd, the waves will not be in phase. In fact, they'll be completely out of phase, like 180 degree out of phase. And if the phase difference is something other than these two, they'll still be out of phase, but not completely out of phase. Now let's talk about the effect of phase between waves when they interfere. Now when waves interfere, there are two types of interference. One is constructive interference and the other is destructive interference. So in case of constructive interference, when two waves have the same frequency and the same amplitude and they exist at the same place, meaning there is no phase difference, then the two waves combine together to form a wave of greater amplitude. Alright, so when two waves combine constructively, their amplitude is going to increase, and the final amplitude is the sum of individual amplitudes of the two waves. In fact, it's going to sound twice as loud as the individual waves. A classic example of constructive interference is amplification. When two periodic waves of same frequency and amplitude have a phase difference of 180 degrees or pi radians, then they're going to cancel each other out as they're mirror images of each other, and there will be no sound. A classic example of destructive interference is noise cancellation in noise-canceling headphones. If the phase difference periodically increases and decreases following a particular frequency, then it gives rise to something called as beating. You can find the link in the description below to check more about beating. Sound generated in everyday life is a complex amalgamation of different frequencies, amplitudes, and phase differences. The individual waves are not completely in phase with respect to each other. At the same time, they're not completely out of phase with respect to each other. It's just a complex combination of different frequencies, amplitudes, and phase differences that gives rise to a final sound that we end up hearing. Alright, thank you for watching this video. I hope you enjoyed it. If you have any suggestions, questions, hit the comments below and I'll be sure to respond. Alright, thank you for watching. Have a great day. Bye-bye.